Welcome to Hananiga High School. I'm Brian Brown, and today we'll be looking at our sixth set of notes dealing with significant digits and measurements. And what we're going to be looking at today is once we've taken measurements and then we do calculations with those measurements, how the significance involved in each individual measurement translates to how good of an answer we can get. In other words, where do we round when we're doing math? Is really what we're going to be looking at. Now, the fundamental idea is an answer can't have more significance than the measurement upon which it's based. So if you have a measurement with a limited amount of significant digits, and we use that in the calculation, that limited significance has to translate to meaning in how good of an answer and how precise of an answer that we can have. So your answer can only be as good as your worst measurement. Now we fundamentally have two different types of math. Addition, subtraction is one style of math. Multiplication, division is another. And how we answer this question, how we determine how your answer can only be as good as your worst measurement is really different with those two math processes. So the first one we're going to look at, and that's what we're going to concentrate on today, is when we have addition and subtraction. Now what you're going to do in addition subtraction, the statement is round your answer to the same number of decimal places as your least significant number. Now what does that translate as? How are we going to end up doing that? Now another way to look at this is you're going to round your answer to the number with the biggest uncertainty. In other words, the one that's farthest to the left if you've lined up the decimal. So sometimes I refer to this as the leftmost uncertainty. Now, what you have to do is line up your numbers like you're going to add or subtract by hand. So the ones columns are aligned with the tenths, which are aligned with the hundredths, and the hundreds and thousands and so on. So the first thing you do is you line up your individual measurements. Now you have to interpret each measurement and find out where the uncertainty is. In other words, where's our estimated digit we've been talking about the last few days. Now your calculator is going to spit out that answer. But literally that answer means 544.12, and the implication is you have 5 significant digits, and your uncertain digit is in that last digit where the 2 is. So it's 544.12 plus or minus 0.01. So the true value should be somewhere very, very close to that. Well, the problem is our individual measurements aren't good enough to claim that amount of precision in a final answer here. So even though that's what the calculator wants to give us, if we assume that that is the right answer and interpret it as we'd interpret any measurement, we may end up with a very inaccurate statement here. So we have to end up with an answer that is both accurate and as precise as possible. So to do that, we need to evaluate the uncertainties. Now in the first number, 124.0, in that measurement, our last significant digit would be the 0. 0 on the right counts when a decimal shown, so that's a significant 0. That's where uncertainty would be in that particular measurement. Now remember, that's in the tenths place. So that's in that first decimal place, which is the tenths place. Now, that means if I'm calculating an answer and I'm unsure about this decimal place, then that means I'm really also unsure about that decimal place down there. Now, let's look at the next digit, 0.12. Well, 0.12 has 2 significant digits, and the last significant digit where my uncertainty would be in the hundredths place, where the 2 is at. So that means this measurement is uncertain to the hundredths. So that means I'm uncertain about that too. Now the last measurement is a 420 meters. Now notice there is no decimal shown. It's understood it's after the 0, but it's not shown. So that means the last significant digit in 420 is the 2. And what that means is, from this particular measurement's point of view, I'm uncertain about the tens place. Now, look at the implications of those 3 uncertainties. The 0.12 means I'm unsure about this decimal place. The 124.0 means I'm uncertain about that decimal place. And the 420 means I'm uncertain about that decimal place. Well, if I'm not sure about the tens, and there's uncertainty in the tens column, how can I really claim any valid knowledge about the ones or the tenths or the hundredths? And that's really how this idea works. Round your answer to the same number of decimal places as your least significant number. Well, it means round to the biggest uncertainty, and the tens is much bigger than the tenths and the hundredths. So I need to round this answer to the tens place. So out of all of these situations here, the one that is most critical and important is I'm unsure of the tens place, so I've got to round to the tens place. Out of all of my measurements, that's the biggest uncertainty is the tens place, which means I need to round it to 4. What we're really doing is what we talked about yesterday. We're going to underline that digit because that needs to be our last significant digit. That's where we're going to round to. So then we look at the next digit to round. Since it's less than 5, that means we're going to round 444.12 down to 540. So when you add or subtract, that's exactly what you do is evaluate where your uncertainties are, and you're going to round to the biggest uncertainty. So all you really have to be able to do is look at your uncertainties. So let's try a few here. So let's say we are adding 5.8887 seconds to 4.24 seconds. Now the calculator is going to spit out 10.1287. Now I need to evaluate my uncertainties. In 5.8887, that 7 is an uncertain digit. That's my last significant digit in that measurement. And in 4.24, that 4 is my uncertain digit. So look at where they're at. 4 decimal place, 2 decimal places. Or another way to say it would be the hundredths place or the 10,000ths place. Well, hundredths is significantly larger than 10,000ths. So we need to round our calculator answer at that spot right there, at 2 decimal places, at the hundredths column. So if I'm unsure based on one of my measurements to the hundredths, and that's my biggest uncertainty, that's where I have to round my answer. So now you use your rounding rules. Next digit is an 8. Well, that's 5 or greater, so that means I'm going to round 10.1287 to 10.13 seconds. Another problem. Now this one I want you to try. So work it through like I did in the last one. So pause the tape here real quick. Work it through and see if you can get the right answer. So 900.3, uncertain to the tenths. 0.774, uncertain to the thousandths. Well, the first decimal place is significantly larger as a value than the third decimal place. So I have to round to the tenths. So 901.074, next digit is a 7. That means I round up, and I get 901.1. Now, if you go to subtract, it works the exact same way. You're just plugging your numbers in the calculator. The calculator will spit out an answer, and then you've got to evaluate your uncertainties to decide where you're going to round to. So 82.6 or 56 is going to round to the second decimal place. 4.7372 is going to round to the fourth decimal place, or it'd be uncertain to. Well, the second decimal place is significantly larger than the fourth, so I'm going to round to the hundredths once again. And I end up with 77.82 because the next digit was less than 5. So I'm going to round it down to 77.82. And remember, we talked about this yesterday. Why is that called rounding down when all we're doing is leaving the 2 the same? Well, remember, it was 77.8228. And 77.82 is smaller than that original value. So that ends our set of notes over addition and subtraction.